The first speaker is Professor Arun Pati. He will be talking on measuring non-Hermitian operator with weak value. Arun.
Talk about how to measure non-Hermitian operator with weak value. So before I start, I wish to I would like to wish Tony a very happy birthday, and this is a great honor to be here and great pleasure. And I thank especially Urvashi and Dipankar for inviting me here this auspicious event. So Tony has been an inspiring, legend over last several decades to several generations. So in this afternoon session, we are going to have several talks on foundations of quantum mechanics, which is also one of the topic which is close to his heart. Okay, so we all know, we all will agree that even after more than 100 years of development of quantum theory, still it continues to surprise us. And quantum theory is based on few postulates we all know, and I won't read all these. What is beautiful about quantum mechanics is it has amazing predictive power. So whatever you predict using these few postulates, somebody can do an experiment and test it. It is just a matter of time or matter of technological development. Today or tomorrow, somebody can do this. Test your ideas. Okay. So what I want to do is, with a brief introduction, I will tell you about non-Hermitian operators and where we encounter these kind of operators in quantum mechanics, and then I will tell you about weak measurement, and then how to measure these non-Hermitian operators using the weak value idea, and then I will give some examples, and towards second part I will tell how to measure this weak value actually without weak measurement using Mach-Zehnder interferometer. And this idea has been actually implemented in Urvashi's lab recently, and then finally I will conclude. So this is mostly based on one of our theory paper which was published in 2015, and this experimental paper will appear very soon this year. Okay, so in quantum mechanics, you know that physical observables are postulated to be Hermitian operators. This is because Hermitian operators have real eigenvalues. Okay, so whenever you do a measurement, you will get one of the eigenvalues. So for that reason, you say that your physical observables should be Hermitian, and also Hermitian Hamiltonian leads to unitary dynamics. So that leads to probability conservation and continuity equation and so on. So you have the beautiful theory, but reality of spectrum doesn't imply that operator has to be Hermitian. Okay, so the converse is not true. Okay, so in fact, long back, way back in 1929, von Neumann and Wigner, they have discovered that non-Hermitian Hamiltonian can have real eigenvalues. Not only that, Bender and his group, they have discovered using pretty symmetric Hamiltonian system that under certain symmetry, those Hamiltonian admit real eigenvalues. So simplest example of non-Hermitian Hamiltonian in 2 by 2 can be written like this, and you see they admit these eigenvalues and they are real for this choice of parameter. Okay, so indeed you encounter non-Hermitian Hamiltonian which admits real eigenvalues. Not only that, there are several examples you can cite in physics. You encounter this kind of operator in open quantum system, in nuclear physics and in quantum optics. Also, you encounter non-Hermitian Hamiltonian as an effective description of subsystem of a complex many-body system, and also you face, when you deal with creation and annihilation operator of the field mode, they are essentially non-Hermitian operators. And if you want to describe measurement process, there is an effective equation of motion with the non-Hermitian Hamiltonian which has been used before. And in quantum information, you whenever you deal with open system, you describe the system by something called completely positive map. So if you are not familiar, don't worry too much about that. Essentially, closed system evolve unitarily, whereas open system they evolve so-called by master equation, which you can complexly write as a completely positive map. It was discovered by Sudarshan, Choi, and Krauss, and others. And in those kind of evolution, you actually encounter non-unitary evolution, non-Hermitian operators. And also, you encounter product of two non-commuting Hermitian operator when you describe the quantum state using Cauchy probability distribution. And this was also found by Dirac in 1945. So now if you ask the following question, can you measure a non-Hermitian operator in quantum mechanics? Typically you will say there is no direct way to measure average of a non-Hermitian operator in a given quantum state. So this may be one of the reasons that measurement of this kind of operator have not found a place in the realm of quantum mechanics. So what we would like to propose is that we find that the key to measurement of this kind of non-Hermitian operator is essentially the weak value. If you can measure the weak value, you can also measure this. So the key idea is following, that average of non-Hermitian operator in a given quantum state is a complex multiple of weak value of the positive semi-definite part of the non-Hermitian operator. This is the essential idea. So based on this, we develop the whole formalism. Okay, so before I tell the main idea, so let me briefly tell about quantum measurement. So whenever you want to measure a physical observable, what you want, your aim is to extract some information about some property of a physical system by coupling to an apparatus. Okay, so you would like to treat both system and apparatus in a quantum mechanical way. So for the time being, you forgot about the free Hamiltonian of the system and apparatus. Just focus on the interaction Hamiltonian, which looks like this. And A is observable of the system of your interest, and P is some observable of the apparatus, which get coupled through this G, and they interact very briefly for a short time. And then you see that system and apparatus initial state will evolve to a final state, which looks like this. So if the An are the eigenvalue of the observable A, then this will look like this. Okay, this is easy to understand. And then in position basis, you see what happens. The wave function of the system and apparatus in final after the interaction looks like this. Okay, so as you can see, they are indeed entangled state because they are in one-to-one correlation between the psi n and phi n. These phi n are essentially x phi of x minus g times a n. So by looking at the apparatus wave function, how much this is shifted from this original position, you can find the eigenvalue. Okay, this is the model of von Neumann, who tried to explain the measurement using quantum theory, but he found that you cannot actually get rid of the collapse postulate, but you can only shift from to another level. So if you will do a projection on this apparatus wave function, you will see this eigenvalue, and then you will get a collapse of the system state to one of the eigenstates psi n. So you see the strong measurement disturb the state irreversibly, and that results to collapse of the wave function, which you are familiar with. So let me tell you about the weak measurement. You can actually tune the strength, that G, okay, that's sitting there in the interaction Hamiltonian. So if it is G small, then you say this is weak measurement. So that will couple the system and apparatus very weakly, and then what you do, you after the interaction you perform a strong measurement, which is typically called post selection of the system state, and then after doing this you see what happens to the wave function of the apparatus. Then that is the whole idea here. So let me tell that how you get the weak value here. So this was the idea due to Arnold, Albert, and Weidmann in 1988. So again you have the interaction Hamiltonian, which looks like this as before. The only thing is G is very small, so this exponential you expand to first order, which looks like this, and then what you do is you do a strong measurement, that is a projective measurement on the system wave function, and collect only that outcome when you get the system state as psi of f. Okay, so upon the conditional outcome, you see what happens to the wave function of the apparatus. Okay, so that phi f in that case will look like this, and this quantity which is sitting there psi I A psi f divided by this psi I and psi f, the overlap. This is called weak value. And then again, because E is small, you can exponentiate it. So this phi f looks like this. And in general, this quantity is complex and can take value beyond the eigenvalue of the observable A, because you see, if you choose psi I and psi f to be very close, almost orthogonal, this can really very large. Okay. So what you can show is that if you look at the position wave function of the apparatus, you will see that the apparatus will get shifted by not by eigenvalue but by the weak value, okay, which is strange object looking like this. Okay. So this is a schematic way of looking at this what is going on here. So the system and apparatus here, and then you evolve by this interaction Hamiltonian. So this I have dropped before. So for the time being, you can ignore this HA and HS, and then you do the postulation at the time t2 and look at the wave function of this apparatus, and then from there you can infer the weak value. So Richard Josa has shown that you can find the real part of the weak value by looking at the position wave function shift, and the imaginary part by looking at the momentum wave function shift of the apparatus. Okay, fine. Now, here it is Hermitian. I will come to non-Hermitian very soon. Okay. Okay. So what is the use of this weak value? So people have found several applications, like recently, not very recently, but in 2011, people have actually measured the wave function of a single photon directly using weak value idea, and you can amplify weak signal, and also you can probe average trajectory of a quantum particle going through double slit setup. This was based on one of the earlier work by Parthoda and Archan, and recently they did the experiment. And also there are other applications like weak value can lead to better quantum metrology and things like that. Okay. So if you are interested, you can look at the review article by Aharnov and Popescu in Physics World, and also by Cho in Science. Okay, so this is a diagram, schematic picture where you see the strong measurement only will reveal one of the aspect of the quantum entity, whereas weak measurement can reveal complementary aspects. Okay. So how do they measure the weak value? The wave function of the quantum entity using the weak value. Essentially, you pre-select the system state psi and measure the projector x, and post-select the system state p, and then this looks like this. So if you choose the post-selected state p0, then up to this constant, this is essentially your wave function. Okay, that's how they measure this wave function of a single particle. Okay, now I come to main result here. So our goal is to measure the average of this non-Hermitian operator in quantum state psi, and as you see, this is in general a complex number. So the main idea is that given any non-Hermitian operator which looks like this, you can write a polar decomposition where U and R are essentially U is your unitary and R is the positive semi-definite operator with this. You can take the square root of A dagger A, and that is essentially R, and U dagger U will satisfy the identity because that is the unitary part. And if you look at the average of A in the quantum state psi, that will look like this. And what you say that let us define a vector phi which is U dagger psi, and then this becomes phi times R times psi. Then you divide by phi psi and multiply here. So essentially this becomes the weak value of the R and then times the complex number. Okay. So what you see from this simple expression is the average of non-Hermitian operator in a quantum state psi, essentially weak value of the positive semi-definite part of this polar decomposition times a complex number. Okay. So if you can measure this quantity, you can measure the average of A by multiplying this complex number. Okay. So what is the procedure? Again, you have the weak interaction and you choose your observable A to be that particular R, which is the positive semi-definite part of that non-Hermitian Hamiltonian or operator. Okay, and by doing this, you can design your postulation in this state, and that will lead to the desired weak value, which you can use to infer your average of the non-Hermitian operator. Okay, so there are several applications you can find, but I'm not going to tell all the details. So one thing I will just flash here, that is you can define uncertainty relation for non-Hermitian operator. Typically in textbook, what you see, you always encounter with Hermitian operators, and you have your Robertson-Schrodinger relation and things like that. But here you can also do similar uncertainty relation for non-Hermitian operator, and that looks like this. Given any two non-Hermitian A and B, the variance in A and variance in B is bounded by this, which is essentially weak value of this quantity. But don't worry about details. Also, you can, using this idea, you can test the new relation which we have proved in 2014, and that relation is we call the stronger uncertainty relation that goes beyond the usual Schrodinger and Robertson and Heisenberg relation, which looks like this. So delta A square plus delta B square is bounded by something like this. So if A and B are canonical conjugate, you will see that this looks like this. And this quantity, you see, this is a non-Hermitian operator, A plus minus IB, okay? And by doing the polar decomposition, you can write this as some U times R, and then that U times psi orthogonal is essentially phi, and then this becomes weak value of this. So essentially this quantity which is sitting there is weak value times a complex number. So by measuring the weak value using our proposal, we can actually test this kind of relation, okay? Not only that, you can also look at you can find useful application in quantum information, like suppose you are sending a pure state through a noisy channel, and that will transform like this, and these are called Krauss operators, okay? And if you look at how good is your final state with respect to initial state, you look at the fidelity, and that looks like this. So if you can measure this kind of average of these non-Hermitian operators in quantum state psi, you can actually measure fidelity. So typically there is no direct way to measure fidelity because you have to do state tomography, and that is more expensive and more involved, whereas here you can, by measuring this kind of operator, its average in state psi, you can actually find the fidelity directly, okay? And interestingly, we find that fidelity and this uncertainty in the Krauss operator, they satisfy this kind of complementary relation. That means if the uncertainty is more, fidelity is less. So this gives a trade-off relation. So if you want to preserve more information through a noisy channel, you should have a less uncertainty in quantum channel. Okay, now I come to how we measure in experiment. So for that, we choose this operator A, which is a non-Hermitian operator, which is essentially a ladder operator, which looks like sigma x minus I sigma y times half. And this has a polar decomposition with U being sigma x and R being this projection operator HH, okay? And in experiment, you can realize this U by half waveplate with the first axis rotated about 45 degrees from horizontal, and this R you can realize by polarizer with the transmission axis set to horizontal, okay? So if you have an arbitrary state like alpha H plus beta B, okay, then this quantity, essentially alpha times beta star, as you can see, this is a complex number, okay? But if you can measure the weak value of R, which looks like this, you can actually infer what is this average of this quantity, okay? So this is a setup that Urvashi and his students, they designed in RRI. So you have the laser, and you prepare a state psi, and then you pass the beam filter. This is essentially Mach-Zehnder interferometer, and then you put U in one arm and R in another arm, and then look at the intensity at the output port, okay? So you see, after passing through first beam filter, the state is something like this, where A and B are essentially the level that particle is lower arm or upper arm, okay? And then you apply U, as I said, U in one arm of the interferometer and R in another arm, then it looks like this. So essentially, in this figure, this is the state after passing through this one, psi 1, and after passing through this is state psi 2, and so on, okay? And then if you allow your state to pass through second beam filter, then the state will undergo a transformation which looks like this, and this epsilon is essentially the relative phase between two arms. Yeah, I should finish in 5 minutes, yes. And then you put a detector in the port D and look at the intensity of essentially the norm of this vector, and then that's what you see here. So the intensity will look like this, and visibility is twice mod Z divided by this quantity. And what is Z here? Z is essentially the modulus of the average of the non-Hermitian operator in state psi. Okay, and if you can infer this, measure this independently, and this find the complex number argument phi, you can measure Z directly from the visibility. Okay, that is the idea. So this is again the schematic of the setup that they have here. So this already I have said. So to get enough data, so what actually they did is they rotated this half wave plate from 0 to 360 instead of 2 degree, and they obtained the weak value of R as a function of the post-later state. And even though we call this post-selection, but actually there is no post-selection, because essentially in the interferometer there is no measurement on the system state. Everything is going through unitary transformation. And so in this process they were able to measure a class of non-Hermitian operator which looks like this. Okay, and these are experimental data. So this is the modulus of the average of this non-Hermitian operator A with the as a function of angle, and this is the visibility as a function of this half wave plate angle that you put in one arm of the interferometer, and you see the weak value looks like this. If you choose the state psi to be half, actually let's do square root of 2, I'm missing here, sorry for the typo here. So 1 over square root of 2 times h plus v, if you choose your input state as psi like this, and then you postulate the system state in sigma x psi, and which occurs at 45 degree angle, somewhere here, you see this is actually 0.5, and the experimental value they find something like 0.501 plus minus 0.005, so it's very close to theoretical value, which is actually half. So this is theory and experiment, they fit very nicely in this experiment. Okay, so this is the essential message I wanted to convey. So so finally I conclude here. So weak measurement opens a new window to reveal different aspects of complementary world, and what we did is try to address the question of measuring average of any non-Hermitian operator using weak measurement and using the interferometric setup. And essentially what we find is the average of any non-Hermitian operator is essentially the weak value of the positive semi-definite part of that particular operator times a complex number. Okay. Then we also had, in our paper we have focused also how to measure the product of two non-commuting operator, and we also tried to prove a generalized uncertainty relation for two non-Hermitian operator, and I also tried to show how you can use this to estimate fidelity of a quantum state passing through a noisy channel. And we proposed a new method to infer the weak value without weak measurement and post-selection. Not only we did that, also we did actual experiment here in RRI using Mach-Zehnder interferometer. So this proposal opens a new possibility in quantum theory. So whenever you encounter non-Hermitian operator, don't be afraid of that. So you can actually measure them. So okay, so this is take home message. So yeah, with that I stop here. Yes.
Any question or comment?
Think about your weak value.
What is weak? No.
Because the weak value which you used is basically a matrix element, right?
Yeah.
Yeah.
So-
Ahano and all used weak value in the sense that it appears in the weak measurement, like if you
Exactly.
Yeah.
So we have two different protocol to measure the average of a non-Hermitian operator. One is through weak measurement, okay, and another one is through the Mach-Zehnder interferometer. So in second setup there is no weak interaction, there is no post-selection, okay. So it just you can infer this same quantity from the interference visibility. So there is no weakness about this thing. Without doing weak measurement, you can still get the quantity, okay. Yeah.